In this module, we're going to take a practical look at how to go about tuning the PID gains for a cam control system. As I've already mentioned, this is really the backbone of the cam control system. If we don't have our PID control algorithm dialed in accurately, we've really got no hope of the cam control system being able to achieve our targets quickly and accurately. For the demonstration today, we are going to be using the Ecumaster EMU Black ECU fitted to our Subaru STi. And of course, every ECU will look a little bit different. The particular parameters and the layout of the software is going to be a little bit different, clearly. However, the reality is that the way the PID control algorithm is implemented and the way we go about tuning and optimizing the independent gains is really the same, regardless of what system you're doing it on. And we'll start by having a quick look at our Ecumaster software here. So I'm on a logging tab at the moment. We've got a log set up on the right hand side and I am looking at the variable valve timing pre-configured log. I have changed this around a little bit just for clarity for our demonstration while we are running with the Ecumaster ECU on our STi, the intake cam control only, so both of the intake cams. We're going to only look at tuning one cam, so here we have our cam angle 1. Actually at the moment we can see it's sitting at its maximum of 49 degrees. Don't worry, you'll understand why that's the case in a moment. In purple we have our cam target, so that cam target coming from this table over here. So again, this is just going to make things a little bit clearer because we won't have intake cam 2 in the mix there, but of course the process we're looking at here, you're just going to rinse and repeat this for however many cams you are controlling. Down at the bottom, just so we can see exactly what is going on, we've got our cam 1 intake valve control, actuator control duty cycle, so we can see that occurring there as well. Over on the left hand side we've got a number of parameters. We're going to go through some of these as we look at them, but we've got our KP, KI and KD, proportional, integral and derivative gain. So I've actually got these zeroed out before we start. Why I wanted to look at these though is generally with most ECUs you're going to end up with a base map or base file from the ECU manufacturer for a cam control engine. Generally this is probably going to be a pretty good starting point, and in most instances the PID gains that they provide in these base maps may be absolutely fine. If nothing else though, they're going to at least give you an idea of the sort of range or suitable range that you're likely to need for that particular ECU, and the range of numbers that we use for the PID gains will vary from one ECU to another. So you can't take the gains that we're going to develop here for Ecumaster, apply these to Motec or AEM or Link or any other system and expect perfect results. They are very dependent on how the particular ECU manufacturer has implemented the PID control algorithm. To illustrate these numbers in the Ecumaster software, let's just bring up our cam 2 parameters. Obviously cam 2, the other intake cam. We'll double click on that and we can see here that we've got a proportional gain of 25, a integral gain of 0.25 and a derivative of 1.25. At this stage the fundamentals of our cam control setup have already been configured. Just a couple of things that I want to touch on here. The first is our cam offset. So this is important that we've got this dialed in correctly, and this just simply zeroes out the cam control system so that we are seeing 0 degrees advance when the cam is not being driven or is in the most retarded position. And we can see if we go across here, at the moment that's exactly what's happening. We've got our duty cycle, which is the cam 1 valve duty cycle down here. That's sitting at 20%, which is our current minimum value, and we can see that our cam position's moving around very slightly. It's never going to be rock solid, but we're basically sitting on our target of 0. We also want to make sure that our maximum amount of advance and retard, retard has been set, and this doesn't have to be rock solid right now. We can adjust this as we go and actually physically measure the maximum amount of travel that the cam does give us. Coming down here as well, we've got our output frequency, which from the default map here is set to 100. Generally a little bit lower than I would normally set, but we'll see how this controls and we may make some adjustments. The key aspects for our demonstration here, we've got our steady state position, which is our open loop duty cycle. So at the moment I've just got this set to 20%. We've also got our KP, KI and KD, which we've got set at 0. So at the moment we are in open loop mode, which is where we want to start. We've also got the ability to adjust our integral limit, our deadband, and there's also a start delay, which is less relevant. The integral limit is there to help us avoid integral windup, which we're going to demonstrate, and the deadband, as we've discussed in the body of the course, basically if we are within 1 degree of our target, the ECU will accept that as being on our target and won't try and drive the system any further. Alright, so let's get ourselves started. What I'm going to do is we'll just get ourselves up and running here, maybe between 2 and 3,000 RPM, just to give us enough oil pressure, and we also want to make sure that before we do this test or our PID setup, we want to make sure that our engine is in fact up to operating temperature, and more importantly that we've run the car long enough to get good temperature into the oil. Given of course that the cam control system is oil driven, it's important that the oil is under what we'd consider at least close to our normal operating conditions. Let's get ourselves up and running now. Alright, we've got ourselves operating at about 3,000 RPM here, and our time graph is operating, and what we can see straight away is our purple line here for our cam target. That's increased now to 8 degrees, and you can see the reason for this is we're now interpolating between our 60 and 88 kPa columns there in our cam target map. So we're not quite on 14 degrees, but we're interpolating between. The green line though, our actual measured cam position, still sitting at 0. Simple reason being that we do have our PID gains zeroed out, so the current system is doing nothing to try and drive us towards that target. So what we're going to do now is start by setting up our steady state position duty cycle, and to do this we're starting at the minimum value I can enter there of 20%, and we're just going to use the up arrow key and we're going to increment that, and we're going to be watching that green line to see when that starts moving. Generally we're going to be close to 50% duty cycle when we can expect the cam position to move, but there's still a range there, probably within normally plus or minus about 5% duty cycle. So let's just step ourselves up here, coming up through 35, 38, 39, 40% duty cycle, so we can see that incrementing on that brown line at the bottom. So still no movement from our green line. It will come up through 43, 44. Okay, so we can see now with 44% duty cycle, our cam timing has started to move, and I've actually just decremented that back down to 43%. So 44% is about the point where we start to see some level of movement. So let's just pause this graph and we'll have a quick look at it for a moment. So this point here, this is where we started to see that cam actually advance. So right before it started moving, we can see that our value there was 44%, and that's when it started to increment up. When I went to 45, it started to move a little bit more sharply. You can see that on the other side of this little sawtooth shape here, this is where I started reducing that back down to 43%, and it dropped. So let's just get our time graph up and running, our logger up and running again. So once we've found that point there, 44% duty cycle, give or take, we can basically play with the cam timing the same way that the ECU does. So 45%, start to see it rise. If I go a little bit higher, you can see it rises much sharper, and likewise if we pull the cam position back, the duty cycle back down, the cam position will come back as well. So the point of this is we're trying to find that position where we just first start to see movement, and for us it looks to be 44 to 45% duty cycle. I'm going to call that 45%. So that's the first part of our job done. It is worth mentioning that while we go through that process, we've got quite large swings in our cam timing. While I've been talking there, we can see we've gone through to maximum, which is about 50, 51 degrees. It's a good time to come down and fill out the maximum value here. This obviously is now different to our other bank of cylinders. chances are the engine's not going to run terribly nicely while that's happening. But it's important to mention we're at relatively low RPM. I've got very little load on the engine, so I'm not going to be risking damaging the engine. It is worthwhile though just keeping an eye on your air-fuel ratio and making adjustments if necessary. Alright, we'll move on now. We'll start having a look at our PID gains. Before we do that though, we'll just mention our minimum and maximum duty cycle. So we can see here our maximum duty cycle set to 90, minimum to 5%. Now generally we're not going to need such dramatic swings in our duty cycle to actually get good cam control. We want to make sure that these are set within the linear range of the actuator's ability to control as well. Generally I'm going to be somewhere around about a minimum of 10 to 20%, a maximum of 80 to 90%, and that's going to give us reasonably good control. And again, if we've got everything set up correctly and we're asking for sensible cam targets or changes in cam targets, we're not going to see the swing out to those extremes anyway. So we'll set those to 90% and 10% for the time being. Right, we'll come down to our KP, KI and KD. I already know that the sort of values we're likely to see for our proportional gain somewhere in the region of maybe 25, 30 in this particular ECU. Before we make these changes though, what I'm also going to do is just come up to our cam target table and we'll set the values all to 0 degrees in the cells that I'm tuning, or the cell that I'm running in, as well as the surrounding cells, so we've got no interpolation. This is important for our step change, which is going to come next. So let's start by entering a value of 10 for our proportional gain. Straight away you can see what's happened there is that our cam timing has dropped down onto our target. We'll just pause that for a moment. We're very close to our target. We're targeting 0 of course, and our cam position being measured as 1.5 degrees, so pretty close. So that's the first step there, but what we want to do now is ask for a cam timing change. Let's come into our cam target table here, and when we're doing this we want to ask for a reasonable step change, probably at least a 20-degree step change. So let's do that now. We'll enter a value of 20 degrees, see what happens. Now we can see we've got response there. We'll just let everything step across a little bit and we'll pause it for a moment. So we can see that our response there is pretty good. We've come up, but there has been a little bit of a slow rise up, in particular as we've got closer to our target. You can see that the cam position has actually sort of smoothed off a little bit. It's actually overshot as well, and it hasn't ended up right on our target. Pretty close, but that's sort of what we can expect to see when our proportional gain isn't right. We'll get our time logger back up and running here. And what we want to do now is make another step change. So generally with the intake cam here, I'll probably be stepping 20 degrees, and I'll be going between 10 degrees and 30 degrees. So let's come back down to 10 degrees. And the reason I want to go between 10 and 30 is it allows us to see the overshoot above and below our targets. For example, if we were going between 0 degrees and 20 degrees, when we step from 20 down to 0, the system mechanically can't overshoot and go past 0 into the negatives. Whereas if we go between 30 degrees and 10 degrees, as we step from 30 down to 10, we might see the cam timing dip below 10 before catching up. So it gives us a really good opportunity to see exactly what's going on there. Alright, so our first change made there, and we've got a reasonable result there. A little bit slow in our response, and we're obviously not quite perfectly on our target. However, that's just the start. So what we'll do now is we'll make our next change. We're going to double our proportional gain element. We're going to go from 10 to 20, and we're going to step from 10 degrees up to 30 degrees again. So we'll press enter and we'll assess our result. It actually looks pretty good, so let's just pause that for a moment and we'll have a look at exactly what's happened. Let's start by zooming in so we've got a better idea of what's going on here. So we can see the moment that our cam target has stepped here, we can see that the green line there, it does step up towards our target. It's still a little bit slower than I expect we can get. We've got this tiny overshoot, although in reality it's actually done a pretty stand-up job. We've gone to 31 degrees and then it's settled back right on our target. We can also see here what the actual duty cycle is doing. So we can see that immediately we step to a maximum value of 70 to get a quick movement initially, and then as we get closer to the target we step back towards our steady state position, and that's just that proportional gain in action. We can see that the further away we are from our target, the larger the result of that proportional gain, the bigger the duty cycle change, and then as we get closer to our target our duty cycle comes back. Alright, let's get our time graph, our logger, working again, and we can now make a further change. I was actually pretty happy with that, but let's try a value of 30 here, and again we'll make our step change. We'll go from 30 back down to 10 degrees here, and let's see what we get. Okay, let's pause that. So here we can see we've got pretty quick response, but we can see we've now got this undershoot and then we've got a quick oscillation. So we've got one single oscillation there, so we're not too bad there. And we can also see the cause of that oscillation is the reversal of our duty cycle there. So this is an indication we're probably gone a little bit far with our proportional gain, but we can drag some of this back by using a derivative for our braking effect. So all's not quite lost just yet. What we're going to do though is just get a bit of an example of what's happening when we have gone too far with our proportional gain. So let's come down here and we'll double this again to 60, and now we're going to enter our step value of 30 degrees. We'll press enter. Right, so now we've lost control of the system. You can see if I pause this, we've got this oscillation in both the green line here for our cam, measured cam angle, and you can see that the reason for this is that duty cycle is just all over the place. So basically 30, we're probably there or thereabouts. We've got that slight overshoot or undershoot, not too bad, and we'll see if we can correct some of that with our derivative gain. So let's get our logger back up and running. We'll come back down and we'll enter our value of 30. So basically, as we've discussed in the body of the course, a good place to start is to make significant changes to your proportional gain. There's no danger of damaging anything here, but we want to find the working range for our particular system. So a good way of doing this is to double our values. That way you'll really quickly creep up on that area where we lose control. So back down to 30, we're going to leave it there for the moment, and what we're going to do is start, we're going to actually move out of order here. We'll skip our integral component and we're going to come back to that. We'll actually work on our derivative now. So let's start by adding a derivative component of 5 here. So on its own right now that's not going to show us any result whatsoever. Remember that works in the respect of the rate of change of error. So what we're going to do is make our step change again. We're going to enter a value of 10, and what we want to do is just analyze what happens when we get that first change. Are we going to still get that overshoot and oscillation? So let's press enter and see what we get. Alright, so that's actually looking pretty good there. Let's pause it again. We've got pretty quick response given the scaling that I'm using here for this logger. Remembering, it's important to be realistic. We're not going to get instantaneous response, and I am asking for a really large cam angle change of 20 degrees instantaneously. It's not going to be possible for it to track that perfectly. So that's important to understand there. So we've got pretty quick response there. We do have a slight overshoot there. So we've got a target of 10 degrees and we've actually gone down to 5.5 degrees. So 4.5 degree overshoot. We quickly pull back to that. It's gotten rid of that continued oscillation that we had initially before we added in that derivative gain. So now we can basically go back and forwards between our derivative and our proportional gains and see what will give us the best result. I'm going to leave my proportional where it stands at the moment, and we're going to try increasing our derivative gain a little bit further. We're going to go up to a value of 10. Again, we'll step back up from 10 degrees to 30, and we can see there pretty good result, all things being considered. We'll pause it and have another quick look here. You can see we've got a very small overshoot there. We go up to about 32 degrees peak, but not a particularly significant overshoot in the big scheme of things, and straight away we're back onto our target. So I'm actually pretty happy with this. If we continue to add derivative gain, what we're going to actually do is end up adversely affecting our response, because the derivative will be acting there to kind of slow down our results, and we don't obviously want that. If we zoom in on our graph here, we can also see the effect of that derivative gain. Let's have a look at the shape here of the duty cycle, and what we want to look at here is obviously in response to the cam change and the error that then is created, we get a very strong positive value there, 81% duty cycle. And then as we get closer, obviously the proportional gain element is reduced because our error is getting smaller. But what we can actually see here is that the derivative gain actually comes in. If we look at the point that I'm at right now, we are still below our target. We're 28.06 degrees measured cam angle with a target of 30. But if we look at what's happened to the duty cycle, it's actually already reversing. It's already trying to slow that cam down because it's sitting at 43% duty cycle. Remembering that's actually less than our steady position duty cycle. So that's the effect of the derivative gain, and it continues to pull back here as I move across there. At the point that we hit our target, the cam actuated duty cycle has been pulled all the way back down to 40%. So that's the derivative gain in action, and we can't get that slowing effect without that derivative gain. Alright, let's get our time graph back up and running here. So at this point we've got our proportional and our derivative gains pretty well dialed in, and we're getting pretty good control even without any integral element. However, we're going to have a look at that integral element now, remembering that's going to help remove that remaining error. So at the moment we've got that value sitting at 0. Remembering from our base values, we're probably expecting numbers here of somewhere around about 1 to 2. So let's start with a value there of 1, and as soon as I do this, we can actually see that we see a bit of a movement in our cam timing. It's moving around here under steady state conditions, but let's do our step change here. We'll go from 30 degrees back down to 10, and we'll see how well everything tracks. So let's just pause everything for a moment, have a look at that. So we can see here that as our cam position is tracked down, it's overshot our target. It's gone down to a minimum value of 5.5 degrees there, so a 4.5 degree error. Pretty quickly pulled that back up, and it sat down around 8.5 to 9 degrees, and then our integral element has moved that back onto our target. Now we're sitting within 1 degree of our target of 10 degrees essentially. Remember again, our dead band there of 1 degree means that as long as we're within 1 degree of our target, the ECU thinks that we're on target, so it won't try and do a better job. So let's have a look at what happens here if we increase our integral element from 1 to 2. So we'll get our graph, our logger back up and running, and again we're going to step from 10 degrees to 30 degrees. We'll press enter, and we can see that we've got that very small overshoot, and we're straight onto our target. We're oscillating very slightly around the target, but we are quite tight on our resolution there, so it's making it look a little bit worse than what we would normally be seeing. That's probably a pretty good place to be, so let's have a look at what happens when we go too far with our integral. So we went to a value of 10 here, and just like a proportional, straight away you can see that that gives us that oscillation. So again, this just helps us find the working range that we can use for our integral gain. So I'm just going to come down here and enter that back to a value of 2. So I've got our proportional, our integral, and derivative values that are working and giving us pretty good control. Let's just try a few more steps, and we'll go back down to 10 degrees. We'll now make some smaller step changes because, as I've mentioned, 20 degrees is a larger step change than we ideally would want to see instantaneously. So let's make a 10 degree change. We'll go from 10 degrees up to 20. We'll have a look at our response. Got a little bit of an overshoot there, so it may be the ability to play a little bit further with the combination of our proportional and our derivative gains, but certainly the response and the amount of overshoot and how quickly that is resolved, this is going to give us really good control, and our cam system will work. Let's try a smaller change again. We'll try 25 degrees. nice and quick response there. Let's pull that back down to 15 degrees. It's important to see how our cam position is responding with both advance and retard commands. So it seems to be doing a pretty good job. A couple of other things that we want to mention here. So our integral gain does work in conjunction with our integral limit. So we do want to make sure that our integral limit isn't so tight that it's clamping the integral element's ability to do its job. This integral limit is there to help prevent integral windup, but if we are targeting sensible values, then the integral windup is not going to be a concern. So at this point we've got our PID gains dialed in, we've got good control over the cam position, everything's tracking quite nicely, and hopefully this illustrates the process that we do want to go through. As you can see with cam control as well, it is actually really easy to make adjustments to those PID gains, because we can sit here under steady state conditions and just command an instantaneous change like this and the system will respond. So in this way, PID control tuning on a cam control system is significantly easier than the likes of a boost control system on a turbocharged engine. For the last part of our demonstration, we'll have a quick look at what occurs when integral windup is happening. To do this, we're just going to be targeting a cam angle that we can't achieve. So let's come back into our cam target table here, and we're into a value of 60 degrees. So straight away we can see our cam angle target goes up to 60, that's our purple line, and we can see that our cam position is sitting at the maximum we can achieve there. It's about 51 degrees maximum. We can also see at the moment, because of the integral windup, our cam duty cycle is sitting at 90%, so it's trying hard to drive us towards that unachievable goal, because the cam control solenoid is sitting, or the cam wheel I should say, is hard against the mechanical stop. So now what we're going to do is we're going to target a realistic value that we can get to, so we'll change that from 60 down to 30, and what we want to do is have a look at our response. So we'll just pause that, and we can see that the cam target doesn't change initially, and we can also see how slow the response is, how slowly our duty cycle drops back down. We don't get that instantaneous result, even though at the moment we're sitting with a target of 30 degrees and we're still at 51 degrees, so a big error there. And we can see how lethargic this is, how it sort of tracks along at the existing cam target and then slowly sort of drops down towards our new target. So just to see what that looks like if we didn't have integral windup occurring, let's do that again, but this time what we'll do is we'll target 50 degrees, which we know we can get to. Nice quick response up to our 50 degree target. We'll now enter a value of 30, the same that we had before, and we'll see how quick our response is. So it might seem like a subtle difference, but you can see how much quicker we get down onto our target there. And if we are targeting realistic values, this is the sort of response we should be able to get, nice and crisp, straight onto our target with no latency in that value, latency in that control. That's all going to add up to a system that's going to respond quicker and more accurately to our target changes. So there we go, a little bit of a rundown on what actually goes into the practical element of PID control tuning, and you can take what you've learned in this module and you can then apply it to your own tuning, remembering of course it's just a rinse and repeat of this process for each of the cams that you've got that do need continuously variable cam control set up. That was just one of the modules taken from our cam control tuning course. If you're tuning an engine that uses continuously variable cam control, switch cam control, or you've fitted vernier adjustable cam gears to your engine, this course is perfect for you. You'll learn about the fundamentals of camshaft operation, and you'll see how the valve timing affects performance, economy, and emissions with dyno demonstrations. You'll also learn some general guidelines for the ideal valve timing events for optimizing both low and high RPM performance. If you'd like to find out more about this course, click the link for more information.